Hello everyone and welcome to this electrodynamics series once again. Today we will look at the third integral theorem in the integral calculus part of this series, and that is the fundamental theorem for divergence. Okay, so yeah, so what is it, it says. So suppose we have a surface. Okay, so this is a closed surface S, and there is a, if it is a closed surface, then there must be some volume V resides inside that surface, inside that closed surface. So what this theorem of divergence says, that if it okay, and one more thing, that we have this V vector field that is present everywhere in this space. Okay, inside that surface, inside that volume, as well as outside of it. So what this says, that the divergence of that field, that vector field V, that divergence of that vector field V, when we take the volume integral over a volume V, and in here we have this volume V, and that is going to equal to the surface integral, and that surface should be the closed surface. Okay, so that volume that get from a closed surface, and we have to take this surface integral of that closed surface. Okay, and that gives the flux that is coming out. Okay, so basically this integral is actually the flux. Okay, right. So what it says, so the flux that coming out from the closed surface S is equal, okay, that is equal to the divergence of the vector field V, and we have to take the volume integral of that quantity, that divergence. Okay, so this is the equivalent statement of this mathematical equation, but let's try to understand it in a better way. Right, so what does it represent? Right, so what it says, that if we have a flux coming out of a surface S, okay, if we have a flux that is coming out of the surface S, then that means that inside that surface, which has a volume V, okay, inside that surface there must be something which has the capacity to produce the divergence, the diverging vector field V. And what is that vector field V? The same vector field whose flux is coming out of that surface. So if there is a flux that is coming out of that surface, okay, so there, that means there must be some source or sink which has the capacity. Okay, so source and sink has the capacity to produce the diverging vector field. Right, and we will try to prove it. Okay, yeah, one thing that I wanted to say over here, that of course it is true for any closed surface. Okay, but I am going to take a cuboid and will prove that that theorem for the cuboid surface. Okay, so in the cuboid we're gonna have this 1 2 3 4 5 6 surface. So we have this of course this surface, and there is a volume V associated inside that surface. Okay, right. So we will going to prove the divergence theorem for this cube, uh, cube, and we will assume that it is going to true it is obviously true for all type of surfaces. Okay, right. Now let's come. Now we will first of all, what we are going to do, uh, we'll first of all we will take the coordinate axis. Okay, we have this x, y and g axis, right? X, y and z. Okay, okay, so let me use the different color. Okay, so I'm using the green color. Okay, so what we are going to do, right? Okay, so we have this cube, and okay, so this all of these points have a different coordinate. Let's say the side of the cube is let's say first of all, let's say this is infinitesimal, not infinitesimal at this moment. We will take the infinitesimal. Okay, so let's say it has instead of cube, let's imagine it is a cuboid. Okay, and it is going to be true for that case also. So it is a cuboid. Okay, so u, so it has a length delta x, breadth delta y, and height delta z. Okay, now there is a one vector field v, which of course which is present all everywhere in this space, right? And that vector field is vx, which is a function of x, y and z, and x cap, plus vy, which is a function of x, y and z, y cap, plus vz, which is a function of x, y and z, z cap. Okay, now so what we have to do, first of all we will calculate the flux that is coming out of all of these surfaces. Okay, so of course we know that we have 6 surfaces, right? So we have 6 surfaces. This is the first surface, and opposite to that we have the second surface, third, fourth, fifth and sixth. Okay, so let's name it first. Okay, so we're gonna have this let's say the first surface, the second surface, we have this third surface, fourth surface, now fifth surface, sixth surface. Now we will take the first surface. So what is the value of v at that surface? Of course, if imagine this is the origin. Okay, so so that must be delta x, right? So on the surface 1, the value of x is delta x.